got to thinking about when I was asked to speak tonight about, this is my story in amateur radio, but almost everything that you're going to see happened before most of you were born. And that really hit me, because all the progress I saw through amateur radio was a very exciting time. I'm not sure that it won't be the same for the new hands now, and that the technology is changing so fast that I think you'll see in 40, 50 years a similar, just, you know, why did it look so hard in the beginning, and how simple it is now. You know, you have DSP receivers in your ear, and it's hard to say what's going to happen. And we certainly didn't know back in the 1960s how far this was going to go. I started out, it's been about 60 years now. I got my call, KN6GSJ. They had novice class then. We had 5 words a minute and a little bit of theory, and it was good for 1 year, and then you had to take another test and get to general class. Well, I was going to school. This was back in 1955 time frame. I worked for the summers, the National Park Service, and we, in the Sequoia Kings Canyon National Park, we had backcountry repeaters for the rangers and for search and rescue missions there. And remember, this was before transistors. So we had radios up in the backcountry in the Sierras, which we put in by a horse and mule, and hand drill all the rock things for the guy anchors. Had to haul A and B batteries in, and we had these repeaters scattered over the backcountry, all interconnected on 150 megahertz, and we had some up at 13,000 feet. This is one looking up the upper Kern River toward Mount Whitney. This is the repeater location. And that's what they looked like back in the days. These were old Motorola pack sets, and they used little pencil tubes in them. And you can see the A and B batteries there, 67.5 volts. A bunch of them series, and a bunch of 1.5 volt A batteries. And the batteries in this application would last just about a month. The repeaters were essentially FM, and there was no what they call private line or digital codes or anything like that in those days. Just carrier. If a carrier received a carrier, it retransmitted it. And so you had a squelch circuit in the radios, which was very critical, because if the squelch loosened up, like on an FM radio there, they would transmit. And once it started transmitting, and it was on continuously, it was good for about a day, and then you had to worry about a 4 or 5 day pack trip to get back and fix it. That was typical of the tubes that were using there. That happens to be the squelch amplifier. But fairly low power consumption, but they did take 67 volts and 1.5 volt filament. And that's off on a typical trek. Got to haul all the batteries and the radios, tower sections, and sometimes it take us 4 or 5 days to get to the repeater sites. Again, most of the repeater sites were very high, so there were no trails to them, so we had to either make our own trails or go across country. We had a dedicated string of 7 mules, 3 horses.
What was the transmit power? What was the power of the tower itself?
I'm sorry.
What was the tower's power?
Oh, these ran about a watt. Yeah, very, very low power. That was a dream job, and I didn't realize how a dream job it was until I left it, because you got essentially paid for spending half your summer in the backcountry, going all over the place. And we'd have what's called front country. There were 3 of us in the radio crew, and one of us would stay behind and take the truck, and everywhere a truck could go, a service truck, the service stuff you did in the mobile radios. And then the other one, a packer, and myself or the other guy would go and on about a 6-week swing through the backcountry and go in at like Mineral King and come out up near Yosemite. So it was pretty sweet. I went to work at Lockheed in 1960 and got involved. At Lockheed in 1960, they were just really getting started in the Agena series of spacecraft. And they had the Agena A, which was the very first Agena series, and I got in just at the end of the Agena A series and the start of the Agena B series. And I met a group of hams there, and almost everyone here is Lockheed based. And these will all be old. You won't know any of these people, but some really interesting people.
Go over.
Yeah. Getting permission to put a home-built satellite on a military spacecraft wasn't easy even in those days. And a lot of meetings. George Jacobs, USIA there, Herbert Hoover Jr., who was president of ARRL then. John Huntoon, another ARRL hierarchy. We had General Curtis LeMay involved there. Senator Barry Goldwater was also involved. And this is getting ready for the launch of Oscar I, the board of directors. That's Oscar I in my backyard. That's when I looked. More hair then. You can see on the bottom there the spring that separates it from the host spacecraft. Some alignment pins, and then on the upper top there you'll see a little hole with a plunger through it. And when you made it to the spacecraft, that plunger goes in, and when it comes off the spacecraft, that plunger comes out and turns on the satellite. These are some of the early builds of the electronics. This was the 2-meter transmitter. Keep in mind, in those days, output impedances, and in fact, there were no transistors in those days which had any power, 150 megahertz, which is where this satellite operated there. So we had some hams at Fairchild, and they were doing some experimental work, and so they essentially designed and made some transistors for us. So these were the only ones in the world at that time. This is one of the keyers, which measure temperature and send out a high rate. There you can see the separation mechanism, a little hook that holds the antenna at the top where my thumb is, and the plunger and spring loaded that goes all the way to the bottom. It's mounted on an Agena B rocket. This is the Vandenberg.
So booster, Thor?
Thor, yeah. And we ended up with a model in the Smithsonian, right next to Telstar and Commercial Courier, some of the early satellites. This is Oscar II. Again, there were no solar cells back then, or very few, and so we were all mercury batteries. And I got to thinking about this shot here, and you see all the Heathkit. You guys, newer guys, won't recognize that stuff, but that was the equipment in those days. You couldn't buy most of your equipment, couldn't afford it, or it didn't exist. And Heathkit had a wide range of kits that you could build, and I wish they had something like that nowadays, because most engineers now are all paper and no hardware, and it's just a shame. So this is assembling the satellite. That's Oscar II. The striping pattern is, you see, is a little narrow on Oscar II. We got temperature data Oscar I, and it ran a little hot. And so we were just learning the whole science of thermal control in space was really new at that time, and trying to balance the sun and the amount of heat that's generated inside the satellite versus the sun.
So those are reflector strips, is that?
Yeah, those reflector strips.
The body is aluminum, just thick aluminum?
Yeah, this was aluminum. And we had some that were magnesium. This particular one, I think, was aluminum. There it is mounted on the side of a Gina satellite. You see the rocket, 50,000-pound thrust rocket engine on the right.
Good operation test.
And you see the antenna's on a spring and bent over, and that little hook grabs it. Now, that whole section of the satellite over the rocket nozzle and up to another 4 or 5 feet and to the left there is all covered by what they call a booster adapter. And it isn't exposed to space until you're well above the atmosphere. What wasn't known by hams at that time were we were putting our satellites on top of the first black satellites that were being flown. And these were the very first imaging satellites. This was back in 1962. And these were all film satellites at that time. And most of this has been just declassified after about 50 years. And it's been kind of interesting because my talk has changed a lot over the years because more stuff gets exposed that happened then, and I can talk about it now.
The unclassified name was Discover for those.
Yeah, with Discover. And they had all kinds of cover stories there. They were flying biomedical payloads where they put a chimp in it and recovered the chimp. And the whole thing was on these. To get the film capsules back, you had to get the film back from space. And so the re-entry process was quite involved. This is a picture of me. I was a test conductor on the Gina B system. There's a place where the Oscar satellite goes. And a pin puller right in there. The pin from the satellite comes through, and a little pin goes in there, and explosive bolt pushes it out, and the satellite ejects. These are the first Corona satellites, and this is a little later model which had a 2-bucket payload, and very complicated film strips that looped around and came back in, and you had to move film, fairly wide, big film. You want to get as much of it on as you can, and yet when you had a two-bucket version, you had to run the film through both of them and yet somehow seal it off correctly, so when you separated and came back to Earth, it wouldn't burn up.
Who was the contractor for the camera?
The early ones were some were Perkin-Elmer and Eastman. These were typical of the orbit tracks for the early satellites. You can see the satellite track is in red, and then the black lines are essentially the path that you could image. Here's some of the details on the recovery vehicles.
So did Lockheed welcome you with open arms to be doing this, or did they do it with some reticence? I mean, how did they feel about this amateur program?
Like I say, building the hardware I thought was sort of the easy part. Didn't seem like at the time, but the real job was done by the politics back in Washington and with the Air Force and things like that to allow us to go on there. Because in the early days, Corona, they had the first 13 failed. First 13 satellites, something went wrong. They deorbited wrong, or they couldn't get the bucket, or like that. And so they were on a very risky path. I mean, they didn't want to incur any more risks, than they had to. But we were able to talk them into it. This was the typical bucket recovery, where you separate the bucket from the satellite, you spin it up for stabilization, fire a retro rocket, you de-spin it, and put a parachute out, and then you catch it with an airplane. You usually caught it with an airplane. They had sea plugs in them. If they went into the ocean, they had a few days, and then the sea plug would open and it would sink. They didn't want the Soviets to recover them. You can see a kind of a trapeze arrangement there, and a cable comes off to snag the parachute.
Timing is everything.
Yeah.
Requires good aviating.
This was near Hawaii, and again, everything had to be right. You had the right orbit. You had to know exactly where you were. When you fired everything, because it made a big difference. Where it landed.
And if it goes into the cloud there,
Then you hopefully there's a plane below it that will catch it. Not all the capsules made it to the right place. This one landed in Venezuela, in the middle of the jungle. Some of the things they did in the early Corona too, they to the public it was biomedical stuff like that, and they said they would fly chimpanzees, monkeys, things like that. And what they would do on occasion, they would the program was public and they opened in the Discover series, but what they were doing was secret. And so they would have these press conferences where the capsule would come down, they'd go in a room, and they'd come back out with this a monkey and a strap in a little space suit like that. And Paul Missoff is This is the E5 imaging payload. You can see part of the retro assembly here. Right there underneath that dome is a very large mirror at a 45-degree angle, and it sweeps back and forth, feeding the video back into the back end of the payload. And that's me doing a test on it there.
Top secret.
top and bottom.
Now you see here, ground resolution 20 feet, 5 feet for this.
Yeah.
Back in those days, that was spectacular. And now,
How would
you can see
Google
the,
Earth compare to that?
what's that?
How would Google Earth compare to that?
Better.
Better.
E5 too. And that was followed later by the hexagon system. And this had four return boxes. This is a huge satellite. And this was recently declassified a couple of years ago, and there's now, there was one of them was presented to the Smithsonian. And there's a little satellite right there, and there's another one on the other side, but you can't see, and I'll come back to that in a little bit later.
Were any of the images declassified?
Yes. You can go on the website now and find a lot of stuff. Again, it's 30,000 pounds, 60 feet long. These are big. That's a picture of one in the Lockheed, one of the Lockheed high bays. And there it is at the Smithsonian. A very good book. It's on the history of the Corona spy satellites. It's here. And after Oscar 1 and 2, which were beacon satellites, they just transmitted a high signal, and by measuring the rate of the high, you could tell what the temperature was of the satellite. And we wanted to get something more adventuresome. This is 1964, and this was the start of the Oscar III satellite. And this was going to be a translator satellite, come in one frequency, go out another. And this was a linear amplifier in the system. And again, you can see the impedance matching in those days was still difficult. You didn't have internally matched devices. This ran at 1 watt linear. And these were some of the other modules built. This was the pulse width keyer we built. And they're little flip-flops, like transistor flip-flops, and stacked in a little cordwood.
Refrigerated surface.
This was the one of the beacon transmitters. We used a kind of an interesting approach, which I still use for a lot of things there. This is double-sided circuit board, and you solder it up inside and outside, but you can isolate the inner foil from the outer. And so, in most of our stuff in those days, you had to have both plus and minus voltages. And so you could use power as part of the ground plane, so you could actually have different voltages on each side of this, and it was easy to, in a low impedance path, to run power to things. This was the IF of the receiver. Notice tuning in here, these were all foamed up, and so you had to have a way to tune them after you foamed them. And it took a long time to get the right foam combination right, so you didn't detune it too far that you couldn't recover.
You got under all grounds.
That's another little antenna tuner. You can see the little vent holes there. This was we chose to do an in-band translator at 2 meters, 100. So only like a megahertz difference between the input and output frequencies. And we know it's going to be tough, but we didn't realize how tough until we started trying to build filters. And this was before we even thought about going in on one amateur band and coming out on another, which simplifies things tremendously. And this was one of several filters we built to try to get input and output isolation. And again, your antennas on your satellite are closely coupled too, so you got everything working against you. This is the side of Oscar III, and this is one of the filters we ended up with. We did have little solar panels here, and there's a little rechargeable battery there and a thermostat on it. And we had a temporary panel on here with meters on it so we could measure the currents and the voltages. And we used these when we're in an anechoic, measure the antenna isolation and make sure it would really work. Because up until then, you had test equipment hooked up to everything, and you never really know until you get it in some artificial space environment whether or not it's going to talk to you or talk to itself. We made the cover of CQ. This is March '65. We had a little test plug there that you could go in and power it and meter some things separately. And we gave Fairchild some credit since they donated the RF transistors to us. And these are Sears tape measures. Now the solar panels were still very hard to get in those days. This is mounted on the basic satellite at Vandenberg. This is a particularly highly classified mission, and I was the only one in Project Oscar which had the clearances for it. So when we sold that we wanted to mount an amateur satellite to this particular vehicle, The documentation I had to supply was essentially what the interface would look like. We built up a mock-up of the frame, which had the mounting pins and all that with it. We gave that to the Air Force, and they built the interfacing structure for it on there. And I put it in my car and drove this to Vandenberg and helped mount it on the satellite. And this was, when it arrived at the launch base here, this was the first time any of the Air Force or customers had seen a satellite. Now, the satellite is essentially covered by a booster adapter which slides over that. And when you go into in here, the satellite's essentially in here. And then when you get into space, this part slips out and exposes the rest of it. So our satellite is essentially covered by this adapter until it gets into space. The told us last time, but we had communications issues on how to let the amateurs know when this thing was going to launch, because it was a classified launch. Launch times were classified, launch dates were classified. So we had a number of rehearsals that we had there to alert amateurs to be ready and test all the communications. We had HF communications. This was before internet and all that stuff. So we had HF communications around the world to try to get everyone coordinated so when they could hear the signal and get ready to listen to it. And we had, I think, 2 rehearsals, and then the third one just happened to coincide exactly with the launch. So. I was at, we had a small tracking station at Lockheed off the main campus, a little 17-foot dish, and we were on the launch network. We could hear the thing go there, and we heard the launch, and it was going up. And the alert came out on the net that it indicated that our satellite had separated, come loose. And that would be fine if we were in space and out inside the booster adapter. But if you're inside the booster adapter, it's going to essentially jam the satellite in there, and the main satellite will never come out. So, needless to say, I was concerned. We found out later that it was a misadjusted limit switch on the satellite side, but God, that was the worst in my career. Everything I was dead meat. Because I was the one that certified this thing was ready to fly. So the structural test was a good friend of mine in structural dynamics, and he'd take the thing and he'd twist it like that. I said, yeah, it seems stiff enough to me. Hit it a few times with a impact tester, and certified it good.
Did you do like
you can't do that now.
you do a vibration test on it?
What's that?
Did you do a vibration test on the satellite?
Yeah, we did some vibration testing.
How about thermal vac? Did you do that?
No thermal vac. These are the solar panels we use, and you notice we made them in those days. And your little slip covers, the individual cells, soldered them up. And you notice on here, they look familiar. This is a P11 satellite, which is a sub-satellite, a big one, that goes on the side. Remember that other picture I showed you, the big satellite, which had 2 of these on it. But we made solar cells in our lab at Lockheed for this satellite, and we managed to find a few spares, and they were on our satellite. So this is an unclassified version of the other one we saw there, and there's one of the P11 satellites there, and another one on there. And these ejected, spun up, and went into their own orbit. And these either had 1 or 2 rocket motors on them, so they could go into a circuit, they could make their own circular orbit. And these were all fast reaction, most of them were covert packages for communications, specialized radar receivers, things like that for the Soviet Union. And we had a quick reaction shop at Lockheed off campus where we built these things. And we'd have various manufacturers provide payloads on a very fast basis. So if there was a new radar they were suspected in going in or something like that, we'd tailor a receiver just for that. We'd integrate it at our facility, test it, and then we had a period of, you could do it in about 6 months time period from the time it says we need to do this to the time you flew it. And this was one of the missions that was on the one we went with Oscar 3. These were very early solar panels on the satellite. And they're 9 March 65. That's the Oscar 3 was on this particular launch, along with the Copy 4 satellite. After Oscar 3, which was successful, the Air Force came to us one day and said, we're test flying Titan 3Cs. 3Cs are still going now, but they're huge, huge boosters. And they were trying to qualify the Titan 3C booster system. And they had been flying dummy payloads to then to test the booster capability. And a Florida newspaper caught wind of the fact that they were flying sand as ballast. You know, you needed to simulate a 1-ton payload, so they put a ton of sand in there. And it got really messy when the paper discovered it wasn't like Florida sand, it was imported from God knows where. It had to be special sand.
Why special sand?
So the government, a little bit embarrassed, which is getting rarer to see these days, went casting about to somebody want to take a risk with us and fly. So they came to us and they said, do you want to fly on this mission? And we said, sure. And we had, nothing. We had no clue, no clue about.
How much lead time did you have?
We had 6 months from zero to be flight ready and do the integration. And the integration this time was getting a little more difficult because they actually wanted to see test results and things like that. So it was, a bummer. So you notice these are the Valent series of satellites, and these were the first nuclear detection satellites that were put into space to look for nuclear explosions. You notice the solar panels on these are triangular. Well, we happened to find some spare solar panels off this satellite, and you notice we built a space frame which was triangular and fit these solar panels. So this is one of those cases where you take what hardware you have and design to it rather than the other way around. For the Titan 3C, we had almost unlimited space and weight available to us, and the only issue we had was the time to do it. And we got the TRW Radio Club group involved since they own the solar panels, or they found them somewhere. And
Surplus.
surplus, yeah.
Surplus.
And this was the kind of a tetrahedron. That's what the satellite looked like for us when that's part of the TRW Radio Club. And that's down inside the top of the Titan 3C, and it fit in this canister. And there were like 7 other payloads that went with us. And we were one of the few that worked, because the satellite, when it went up, everything was fine until the third burn, which circularizes the orbit, and the third burn didn't occur. So instead of a 22,000-mile slow synchronous orbit, which we were hoping for, everybody was hoping for, we went in a 22,000 by 100-mile orbit. So just,
Highly electrical.
Yeah, we'll need
and
it.
highly electrical. And we had been looking forward to the synchronous orbit. They're hard to get rides to synchronous. And because this would finally eliminate all the tracking issues we had, getting information out. Again, pre-internet. You know, you wanted to disseminate where the satellite was going to be and all that information. So here was going to be one you could just put your antenna at it, you know, work for hours. Well, since we were at, this was at 450 megahertz, and we had a fairly wide beam antenna, single dipole. And a lot of the other payloads that went with us on a risk basis had highly directional antennas up in the microwave region. And they had almost no hope of being heard because their whole antenna patterns, everything was wrong. And the story that goes along with this is that we found our satellite very quickly because, again, we had lots of hands listening for it. And this was a public launch, too. We knew when everything, you know, we knew when it was going to go. In fact, we were at the Cape at the time. And, oops. And we had to resurrect a orbital dissemination set up at the Foothill Club to kind of tell people where this was going to go. And because there was no ephemeris that came out for this thing for several days. And so we had amateurs that would listen for it, and when they heard it, would tell us when they heard it. And we had most of you won't remember, but the National Geographic used to make an inflatable globe. It was about like that. And we set one of those up on a tripod and got a very large step ladder, and we made an orbit out of wire that was in scale 22,000 miles by 100 miles. And then we could rotate the globe under that. And then as we got a report that says, I started just hearing it maybe from Europe, you could stand up on the ladder, look down from the satellite view, rotate the globe to where you just saw the location of the station that just started hearing it. Then we refine that over a little bit of time and get more and more reports. And finally we could anticipate who should hear it and when. So that was kind of fun. That's what the Titan 3C looked like. The group of Australians contacted us and said, we said, sure. And then they said, how do we do it? And so I have a correspondence file which is about 2 inches thick, and we did this by mail. Again, this was, you know, pre-fast communications. And we used the same structure we used for another satellite coming up, Oscar 6. And they put together a 2 meter to 10 meter satellite, and 3 principals came over here, delivered it, and if you open up the top there, it says, "God save the Queen." This is Jan King. He's just locating recently in this area, but he was the head architect for the AMSAT group, which is still the major satellite organization now for hands. And this was the Australian satellite. Some of the hardware.
Did you have metric versus SAE problems with the Australian?
No.
Why did everybody love
And you can see these were 10 meter antennas, so they were very long.
60.
That's the same structure we used for Oscar 3. We used that design for quite a while, and you can see the 10 meter antenna folded up in there on the shake table. You don't realize how kind of terrifying it is when you put so much time and energy into building this and wiring it there to see cretins put this on a machine, hit the red button and say, let's see what happens.
Better here than after pay.
That's Oscar 7, I think. This is another one we were looking at. I found a source of some solar panels, so I started designing another satellite. We talked with AMSAT, and we were helping them. Our military launches had sort of run out, and so we were looking to NASA to get flights. And the AMSAT organization is based in Washington, D.C., and so they had a lot of contacts within the industry there, so that's where we started getting a lot of rides. We decided to try to modularize some of the stuff because everything up to that point was sort of one of a kind. And these are boxes that I built in my home shop. These are magnesium enclosures for various electronic things that fit in this called space frame. And you can see the modules in here. And the modules were set to, we kind of figured out what the minimum maximum size should be. Battery minimum. And then I would make these and then ship them out to the AMSAT group. This is one of the modules with electronics mounted in it. And again, now when you went to the designers, the guys in Germany, whoever's going to design a particular item for the satellite, we could give them hard dimensions. Here's exactly, it must fit in this envelope. And that's what it looks like when I'm packaged up. That's at the launch base. This one had retractable or deployable antennas, so instead of folding, a little motor mechanism drove it out. I still had hair there. This one here, you can see we're kind of mounted on the outside, but there's, again, a booster adapter which covers the Oscar 8. We use that same design, only this is a too high version for Oscar 9. And that was where I worked on hardware for AMSAT and Oscar till I guess 10 and 11, and then I sort of backed out. But another thing that was going on at that time was this was the first FM repeater in the Bay Area. This was 1962. This was located on Mount Umanum, and it's in an old naval footlocker. It's 3,300 feet elevation, and all tube stuff. And again, this was back in the days. And the first thing we learned is shielding, and had everything very well shielded. They didn't have duplexers and stuff in those days yet, so we had to build our own. And these are sections of 50 ohm coaxial waveguide, which Taylor Howard managed to get for us from the Stanford 150-foot facility. So we take sections of this, and put caps on it and put tuning on it, and hope the copper expansion contraction didn't detune it too much. And the second thing you learn after shielding is that you need ventilation. So after about a week in the summer, there was transformer tar raining down inside. This was a few years later, and we actually spiffied stuff up a bit. This was back in probably 1970. Had a rotatable 10-foot dish, TV Vidicon camera, again, before solid state. The light on here is a 1,000-watt light, and the mount is off a British bomber landing light, which so we could elevate the light, and then the whole thing turned. And then the dish also was remotely tunable. And this 2-meter antenna was remotely tunable.
Where was this located?
Mount Aluminum,
Oh,
behind San Jose, where the old Air Force facility. And our telemetry back in those days were, we had a cable, drop here, and pointer right there.
Direction.
And then depending on where the antenna is pointed, then you focus the TV camera on it and you get real time.
I'm still thinking.
Went into Fresno.
And now on our repeaters, we have like 50 cameras on all the mountaintops around here, and everything's, you could use D-Days and all that stuff, but it's just as easy to have a meter on there and have a camera. And it's just, it's so simple. And we had a high power, had a microphone, a high power loudspeaker on there. We could talk to interlopers on the hill, things like that. And a weather station. And I got involved with Taylor Howard, W6HD, in the early days here, and I came up when they had the log periodic array running down the hill, which some of you may remember or seen in old pictures. And we had a Heathkit single sideband exciter, and we were doing moon bounce, and I was like 20, 25, something like that, and to be able to take a microphone and say, hello Earth people, and have it come back at you was just awesome. And for the new hams that are here, I hope that you will get involved in some form of hardware work. Build almost anything, but learn how to solder, learn how to tune a circuit. It's almost passé now, but I think it's invaluable to get the more practical side of this than just book knowledge. This is a parametric amplifier I built at 222 megahertz, and this was in 1965. So that's it. Thank you.